12.2 Newton's first and second laws of motion. Why do some cars accelerate faster than others? How does an ice skater glide far across the ice after pushing off only once? The answers to these questions involve the concepts of mass and inertia. Aristotle, Galileo, and Newton. Modern scientists understand the relationships between force and motion. However, it took 2,000 years to develop this understanding. Aristotle. The ancient Greek scientist and philosopher Aristotle made many scientific discoveries through careful observation and logical reasoning. He was not always correct. Aristotle incorrectly proposed that force is required to keep an object moving at constant speed. This error held back progress in the study of motion for almost 2,000 years. Galileo. An Italian scientist, Galilei, experimented to find out about the world. By rolling balls down wooden ramps, he studied how gravity produces constant acceleration. Galileo concluded that moving objects not subjected to friction or any other force would continue to move indefinitely. Galileo's portrait and the title page from the book that presented his work are shown in Figure 10. Newton. In 1665, the plague broke out in London, forcing Isaac Newton to leave Trinity College in Cambridge, where he was a student. Over the next 2 years, Newton built on the work of scientists such as Galileo. He published his results many years later in a book titled Principia. In this important work, Newton first had to define mass and force. He then introduced his laws of motion. Newton's portrait and the title page of Principia are shown in Figure 11. Newton's first law of motion. Newton summarized his study of force and motion in several laws of motion. According to Newton's first law of motion, the state of motion of an object does not change as long as the net force acting on the object is zero. Thus, unless an unbalanced force acts, an object at rest remains at rest, and an object in motion remains in motion with the same speed and direction. For example, a soccer ball resting on the grass remains motionless until a force is applied to it in the form of a kick. The kicked ball begins rolling. Because friction between the grass and the ball acts on the ball as it rolls, the ball slows down. The force of friction slows the ball and brings it to a stop. Newton's first law of motion is sometimes called the law of inertia. Inertia is the tendency of an object to resist a change in motion. In other words, an object at rest tends to remain at rest, and an object in motion tends to remain in motion with the same direction and speed. Note that as the soccer ball sat motionless in the grass, the forces acting on it were balanced. The ball remained at rest until an unbalanced force acted on it. The ball has inertia. Think about what happens if you are moving in a moving car that is involved in a front-end collision. The collision makes the car stop suddenly. What happens to you? Because you have inertia, you continue to move forward. The series of photos in Figure 12 below show you how dangerous a front-end collision can be. If a seatbelt and airbag had not restrained the test dummy, it would have crashed into the steering wheel and the windshield with a great force. The seatbelt and airbag work by exerting force against the body of the dummy, opposing its forward motion. Newton's second law. How do unbalanced forces affect the motion of an object? An unbalanced force causes an object velocity to change. In other words, the object accelerates. For example, you apply a net force to a ball when you throw it. The harder you throw, the more the ball accelerates. In fact, the acceleration of a ball is directly proportional to the net force acting on it. If you double the force, the acceleration of a ball doubles as well. Newton has also learned that the acceleration of an object depends upon its mass. Mass is a measure of the inertia on an object and depends on the amount of matter the object contains. According to Newton's second law of motion, the acceleration of an object is equal to the net force acting on it divided by the object's mass. Thus, doubling the mass of an object's cut cuts its acceleration in half. Newton was able to put these ideas into a single formula. The acceleration of an object is always in the same direction as the net force. In using the formula for Newton's second law, it is helpful to realize that the units, newtons, kilograms, and meters per second squared, are equivalent. The math skills box reinforces this relationship. Note that Newton's second law also applies when a net force acts in the direction opposite to the object's motion. In this case, the force produces a deceleration that reduces the speed. This is the principle used by automobile seatbelts. In a collision, the seatbelt applies a force that opposes a passenger's forward motion. This force decelerates the passenger in order to prevent serious injury. The shopping carts in Figure 13 further illustrate Newton's second law. What happens if you push on a single shopping cart? The unbalanced force causes the cart to accelerate. What happens when you push with the same force on a chain of 8 shopping carts? The acceleration of the chain of carts is much less than this of the single cart. The chain of carts accelerates less because it has more mass. Weight and mass. Do you sometimes talk about weight and mass as if they were the same thing? Although related to each other, mass and weight are not the same. Weight is the force of gravity acting on the object. An object's weight is the product of the object's mass and acceleration due to gravity acting on it. The formula for weight is mass times acceleration due to gravity. The weight formula is basically Newton's second law. However, weight is substituted for the force, and acceleration due to gravity is substituted for acceleration. In other words, weight equals mass times gravity is a different form of acceleration equaling force divided by mass. That is, when the equation is solved for force, force equals mass times acceleration. The value of g, gravity, in the formula is 9.8 meters per second squared. In using the weight formula, or Newton's second law formula, make sure that the units are correct. The force, either F or W, should be in newtons. The acceleration, A or G for gravity, in meters per second squared, and the mass, M, in kilograms. The following example shows you how to use the weight formula. If an astronaut has a mass of 112 kilograms, what is his weight on Earth where the acceleration due to gravity is 9.8? You would just take his mass, 112 kilograms, and multiply it by gravity, 9.8. As a result, the answer would be 1100 newtons. That would be his weight due to our gravity. If you study the weight formula, you will see the mass and the weight are proportional. Doubling the mass of an object also doubles the object's weight. Mass is a measure of inertia of an object. Weight is the measure of force of gravity acting on an object. Consider the same astronaut shown on Earth and on the moon in Figure 14. On the moon, the acceleration due to gravity is only about 1/6 that of the Earth. Thus, the astronaut weighs only about 1/6 as much on the moon as the Earth. In both locations, the mass of the astronaut is the same. So basically what that means is this is the same person. They have the same mass. Here on the Earth is pulling down at a much stronger gravity than that of the moon. Therefore, you take the mass times 9.8 and the mass times 0.88, or whatever the moon's gravity is, 1/6, okay, and that would give you the weight. 12.2 assessment questions. 1. State Newton's first law of motion in your own words. 2. What equation states Newton's second law of motion? 3. How is mass different from weight? This concludes 12.2 Newton's first and second laws.